service route network analysis to support local traffic. Ivana Stromov, National Aviation Institute. Ivan, we cannot hear you.
Okay, sorry. Could you hear me and could you see my screen?
Yes, it's okay, please.
Okay, actually now I would like also to present another results of our study in Air Navigation Department of National Aviation University. And in this study, we work on analysis of air traffic service road network to support local air traffic in Ukraine. The main reason of that, as you know, that air traffic is always grows, beginning from beginning of aviation from 1970. Each year we've got growing of passenger flow until, of course, coronavirus disaster. However, nowadays this diagram is going up, and probably in next few years we reached pre-pandemic levels of air traffic. And the main reason of them is that aircraft usually flow by particular air traffic road network. That's why in aviation we use road network like in our road network. And in this case, aircraft can use this air traffic network to fly between airports. And based on different parameters like accuracy of positioning system or applying some risk values, the space which is segregated for each aircraft may be different based on aircraft type and based on some other parameters. And the idea, if we have too many aircraft in future, current air traffic network may catch a problem because it cannot support a particular level of air traffic. It connects also with different problems. It connects with existing network topology. It connects with human factor, and it connects with air traffic controllers possibility, and of course with equipment which serve air navigation, in particular airspace. Actually, here you can see the national flight road network of Ukraine, and you can see that there are a lot of blue lines, and aircraft can fly only by these roads. That's why it means they cannot deviate in the left or in the right side. That's why they always have to follow particular pre-planned trajectory. And I don't want to talk you too much about types of these roads, types of airspace. The main here is that there are different widths of flight roads, and this width of flight roads depends on performance of navigation system. Everything is quite easy. If we have quite precise positioning approach and redundant approach for positioning, it means that we can use quite small widths for air traffic road. If we have low precision and low needs of air traffic, that's why we can increase width of flight road. That's why, for example, in Atlantic and airspace over the ocean, we can use quite wide flight roads, and under the continents we use quite slim flight roads. And it depends on backup positioning technology, because we know that global navigation satellite system is good. However, we need to always have some standby approach. For example, distance measuring equipment, very high frequency omnidirectional range, and other navigational aids on the ground. In aviation, we have a specific concept which called performance-based navigation. And according to this concept, we consider different specification for navigation, and each of these specification has a particular value for flight road width. For example, if you talk about ocean flight road width in horizontal plane, it's like 93 kilometers. If you talk about continental flight, this flight roads is only 13 kilometers. That's why it depends on airspace structure, and it depends on navigation possibility that we can have in this airspace. That's why in our research, we've got a database of Ukrainian national flight road networks. It is not a secret data. It is published in IEEE, and it includes in different databases. That's why we create like our own database of Ukrainian flight roads network. Then we try to create a graph with this network, and then we, in this research, we provide analysis of this graph to support local air traffic. First of all, we count a total length of flight roads in this network. And here you can see length of flight road in nautical miles based on altitude, because each flight road has different application in different altitudes. That's why we analyze the whole airspace and make different levels, different layers for our networks. Then we try to compare frequency distribution of edges in our network based on length of this edge and frequency of how often it appears. And you can see that in most cases we have approximately edges between 25 and 75 kilometers between nodes in our air traffic service network. Okay, here you can see the main description of this network. Thus, you can see that we use order of graph is 381 and size is 571, which means that we use 381 node or waypoints and 571 edges in our graph. To specify this graph, we use agency matrix. You can see it here. However, it is just representation. It is binary matrix, which represents relation in our graph. And for detailed analysis, also we use weighted agency matrices by distances of between waypoints or lengths of edges. And here you can see results of node degree estimation for each waypoint which we have in network. Also, we can set up like 5 the most connected waypoints in the network. Okay, you can see title of these waypoints here. Okay, then we count weighted degree of node for this network, and weighted degree represents how network is widespread, or how many connections to each node we have. based on distances to the closed waypoints. Also, you can see that there are some nodes which is red, which means that if we apply a particular level of air traffic, these nodes may produce some overload stages. However, using only this air traffic service node network is not the full analysis, because actually in aviation we use airports to reach air traffic roads network and then to perform flight. That's why if you would like to analyze potential of our road networks to support local traffic, that's why we need to consider network of airports with the network of flight roads. In this case, we use 16 international airports. You can see identification of these airports and location of network of these airports. And then we apply Poisson air traffic for each waypoint of airport to reach different combination within airports network. And 16 airports give us 120 pairs of combinations of airports, and we apply Poisson air traffic simulation, and then we've got that the most useful waypoints in our network based on the shortest path in the flight roads network are Minirov waypoint, which participates 30 times in the shortest part between pairs of airports. Then Ivano-Frankivsk and Kryvyi Rih. And also you can see here a representation of participation of waypoints in the shortest path between combinations of airport in air connection for support local air traffic in Ukraine. And probably for today that's all. That's why it's conclusion you can see on my slide. If you have any questions, I will be glad to answer.
Okay, thank you very much, Ivan. It's interesting that you check the European part of road networks, because as we know, all roads lead to Rome, and you can check, is it true or not, that all roads lead to Rome or not to Rome. Now it's to Nirov, I think so.
Yes, yes, something like that.
Yes,
and probably if in future our Ukrainian air traffic service provider will consider improvement of network, probably they will they will try to think about the better way to optimize the network, because before the war, for example, air traffic with Russia was absent, and that's why our eastern part was under the load. However, part of network under the Black Sea was overloaded, because all the European traffic goes through the Black Sea, because in this case it is like a wall of Russia, because beginning from 2014 we do not have connection with direct connection with Russian, and also European country does not fly to Russia over the Ukraine. Okay.
Yes, because we have bad experience. Okay, do we have any questions, dear colleagues, dear scientists? Do you have questions to Ivan? Okay, if we don't have, then Ivan, thank you very much for your report. And
Okay, thank you very much.
we come to the next paper. It's a data model and methods for